Good morning all, and thank you all for coming. My name is Alexandre Grad, and I'm from the technical department at Jocavi. I'm an industrial designer, and what you just saw was an installation of the acoustic shell in the Casino Estoril in Salon Preto e Prata. So I'll be addressing the question about why do we need acoustics. But firstly, let me thank our distributor in Singapore, G-Acoustics, for his kind invitation. We very much appreciate. So, talking a little bit of our company, Jocavi was first established in 1992 as a manufacturer of acoustic products dedicated for the professional audio industry. Our application areas vary from auditoriums, concert halls, pavilions and multi-purpose halls, cinemas and theaters, commercial and cultural buildings, industrial spaces, public and office spaces. Also to audio and video studios, and radio and TV broadcast stations. So the most common acoustic problems that we face in the rooms are the resonance low frequencies that we see there in green. So these frequencies tend to accumulate in corners, and that gives us one very annoying effect, which is the 50 Hertz resonance of. Then you have the standing waves and the stationary resonance frequencies and harmonics. Those harmonics and frequencies tend to get multiplied during when there's a fluttering echoes and parallel walls. Propagation of vibrations to the structure is another problem, and of course inadequate reverberation time. When the sound is emitted, there are several different reflections. The first reflections we see there in red. Then there's the second reflection on the second wall, which is in orange. And then there's a third reflection, which we see there in yellow. So this is the natural behavior of sound. It can scatter along the room and being reflected. And the question is, we don't want to hear those reflections, we just want to hear the original sound so that the message is clarivident. The major causes of these are the rectangular room shapes, wrong room dimensions, meaning the proportion between the height, the width and the depth of the room, and the parallel walls, floors and ceiling, and a large surface that normally tends to have to not be acoustically treated, and inadequate interior finishing materials. So most of the rooms have different problems, and in those different problems we need to point out where are the main things that we need to address. So for every sound that we emit, there are different frequencies, and those different frequencies have different reverberation times. So if the difference of the reverberation time across different frequencies has a very big interval, we can characterize this as an unbalanced room with poor reverberation time. On the contrary, if you have a balanced room, that difference tends to be as less as possible, as close as possible to a flat line. That will be the perfection, which is, of course, unachievable. What we can do as humans is tend to get there, and the interval in which we should be working on would be around 22%. And when the variation between the highest and the lowest point is within 22%, we say that the room is balanced. And the room is balanced means that the intelligibility inside that room can make us understand the message. So intelligibility of the room is exactly that. We live in a civilization that cannot sell products without communication. We cannot learn without communication. We cannot teach without communication. And that effective communication only has a way to be done, and that is with clarity of speech. If that isn't there, intelligibility is not there, and imagine how your financial world would be, or your educational world, or business-wise. So these are things we need to address. For the small rooms, it's quite simple to obtain a very good balance, even better than 22% for small and mid-sized rooms. While for big rooms, often becomes more difficult to obtain this value due to a large volumetric in the room. So in those cases, a little bit above, values a little bit above 22% can be used in specific cases, which I'll explain a little further on. So here we have the dead rooms that Ganesh was talking about, which goes normally for between 0.2 to 0.8 seconds until 1. And then we have the medium rooms that goes from 1 to 2 seconds, and the large rooms that goes around between 2 to 3 seconds. So normally a big pavilion should not have, as you have all experienced somewhere in your life, around 10 or more or 7 seconds. The arena or the large pavilion should have a maximum duration time of no more than 3 seconds. So what is the reverberation time? When sound collides or is being emitted, it collides with the materials in the room. It gets bounced back. And there's a decay between the emission and the recession. That's the time that the sound decays, takes to decay 60 dB, we call the RT60. So here we are seeing different types of venues, and in those venues you can see the volumetric of the room. You can see for 5 fundamental frequencies the RT values for each specific frequency. And if you look at those values, they do not vary much from one another. So if we have one value at one specific frequency, the adjacent frequencies need to have closer values to this, between the 22% that we spoke. One example, the Carnegie Hall in New York has 24,000.3 cubic meters with 2,800 seats. The reverberation time is between 1.4 and 1.8, so the difference is 0.4. Take a look at the volume of the room. It's 24,300 cubic meters. So the precautions or instructions that we need to address before going to acoustics are: check, of course, the reverberation time. There are tools for that, and that is one. Check the room dimensions proportions on the Jokavi room dimension calculator. So when you go to the Jokavi website, you just scroll down until the bottom and you search for JRDC dimension calculator. And then you will insert your room dimensions, and with that the software will tell you if you need to adjust any specific proportion dimension, like reduce a little bit the length between this and that value and not above these values, so that the room is prepared and proportional, so that we don't get room modes problems. So you should check the room modes for axial, tangential and oblique reflections. Avoid the parallelism of the walls, surfaces, floors, ceilings, walls, and simulate the room by numeric ray tracing calculations. To do this, you can use the Jokavi acoustic simulator, also in the Jokavi website. It's on top of the menu as Jazz. Jazz, it's the name, Jokavi acoustic simulator. I'll talk a little bit more about it at the end of this presentation. So how do we resolve the acoustic problems? we address the first reflections of the walls and absorb some and diffuse others. We take the low frequencies that resonate in the corners, and we absorb them. We use low frequencies absorbent that are tuned to a specific interval frequencies to get the maximum performance, so that with the proper panels, the proper models and panel placement, we can address these issues and resolve the acoustics of a room, making it more balanced. In here you have an example of one of our high-end diffusers. This is made in porcelain, also available in glass reinforced plastic or GRP, with an average diffusion of 0.67 square meters, 0.67 per square meter, and at an interval between 100 Hz and 5 kilowatts. So these are 100% recyclable materials. From ATP brand, the cost-effective brand, is another example. So this is a mix between diffusion and absorption. It uses two completely different materials to make two different purposes in the room. One is to diffuse with IPS materials, and the other is to absorb with melamine foam. So for acoustic shells, we have a new product, and this is a very specialized high diffusion panel. It comes in two different models, and it's manufactured with recycled IPS, high impact polyester, for being very robust and rigid, which adds for a good dimension stability, recyclability, fire specs, of course. So these models are 15 by 15 by 15 models, which can be repeated across several directions. And there are here two models. One model is the wide diffusion, and the other model is the compression model. Here you can see the diffusion and absorption curves for the compression model. So there are two effects, and the way that the panel is mounted, based on the model, on the top we can see the wide diffusion model, and on the bottom the compression model. So what's the difference? The first one on the top is meant to widespread the angle so that the sound is scattered to the audience that is near the stage, while the other one below, the compression model, it tends to close the angle to project the sound pressure levels to the farther away regions of the audience, so that the front of house engineer can do for the first time in his life, which is to direct acoustic sound without being amplified, and take that sound pressure level exactly to the points in the venue where that room was completely dead. So this allows us to tilt the acoustic shell, and you can choose the other model, the wood model, or this, or combine the compression and diffusion model. So with those combined, the front of house engineer can project the sound to specific areas of the room. It can tilt the rigging structure, and of course we can adapt the design to wherever venue you have it ends through acoustics. So these are some of the international works that we've done across the world, thanks to our distributors around the world. So this is in Turkey, this one's in Portugal. So there is rooms that vary from all types of rooms, from arenas to concert halls, to cultural spaces. In this case, it's live music room, and in that ceiling they have a problem. The problem was that the ceiling was in metal. when that happens, the sound behaves in a strange way. So we use absorbent materials in there so that people can play concerts in the room, and the room can have 2 to 3 concerts a week. Here there is a kindergarten that tends to be a lot noisy, so we need to absorb here with some degree. And here is the Meu Arena, Salatejo. So this one is, what you see here on top are acoustic absorbent materials, which is called a water coat. And all aside from the room, there's an acoustic curtain that is suspended on a truss, mounted on the floor, and lifted up so that inside the room, exactly like this, we can divide it into 3 different rooms and make 3 different gatherings, shows inside the room, but not let one event disturbs the event that it's on the other room, to divide as acoustic barrier. You have a case study exactly on the acoustic curtains available on our website that describes in depth this situation in this work. So this is a food court, which again is the same type of situation, like metal and glass ceilings that needs to be absorbed, and the planetarium. So once again, thank you very much for your time. We also would like to thank G-Acoustics, this geocavity distributor for Southeast Asia, for having us, and have a very nice day. For any questions that you may have, we have a booth on the corner. Please feel free to visit us anytime. Thank you very much.